Okay, I said in the last video I would show you a halide exception, and here it is. So the top reaction is an electrophilic nitration of anisole. So oxygen has lone pairs on it, directly bonded to the pi system, so this is a strong electron donor. It's an activating group, and it's an ortho-para director. So this reaction is going to put a nitro either para or ortho, right? Ortho-para director because it's an electron donating group. And it's fast because electron donating groups are activating it. And if you think about this, right, the benzene in this reaction is a nucleophile. So it's attacking NO2 plus. So the arrow is going from the benzene to the NO2 plus. So if the methoxy group's pumping electrons into the benzene, that benzene's going to be a better base, a better nucleophile. So it's a faster reaction. If you have methyl benzoate, so this is an ester, that carbonyl, the carbon that's bonded to the pi system is partial positive. So this is an electron withdrawing group. Right? Again, the benzene is reacting with NO2 plus. Okay? But the electron withdrawing group's pulling electrons out of the benzene. So you've got, you want the benzene to be a nucleophile, or the benzene is a nucleophile. If you pull electrons away from that nucleophile, it's not as good a nucleophile. And so the reaction is slow. We'd say the electron withdrawing group is deactivating. Just as we'd say an electron donating group is activating. Right? And based on the electronics based on where the electrons are here, an electron withdrawing group is going to put the group meta. All right, and that's almost always how it's going to go. An electron withdrawing group is going to direct meta, and it's going to slow the reaction down. An electron donating group, either weak or strong, is going to direct ortho-para and accelerate the reaction. The stronger the donor, the faster the reaction. So a methoxy benzene reacts faster than methyl benzene. All right, so what about a halide? So if we look at this, chlorine's got 3 lone pairs. That looks like methoxy. So you might say electron donating. And then you would say ortho-para. But I've said this is an exception, and so you're probably sitting there wondering, or you've looked at the book. So the answer is it's ortho-para directing. The lone pairs on there make it direct like an electron donating group, but it's slow. All right? So yes, it's ortho-para directing, right? You can push electrons in, and those electrons pile up at the ortho and para positions. But that's by resonance. The inductive effect, actually the resonance effect, the carbon-chlorine bond, right? Chlorine's third shell, oxygen's second shell. So the chlorine here, this carbon-chlorine bond is actually a little longer. Right? And the orbital that the lone pairs are in it's bigger. The orbital that the lone pair on chlorine is in is bigger than the pi orbitals in the benzene. So they don't overlap as much. All right, so there's poor resonance overlap. Orbital overlap. So induction is more important. And if you think about induction, right? You learned this in Gen Chem. The carbon-chlorine sigma bond is polarized strongly to the chlorine, right? So chlorine, bromine, iodine are all electron withdrawing. So the net result is they direct like they're an electron donating group, right? So they're going to direct ortho and para, chlorine, bromine, iodine. But they are not electron donating groups because they slow the ring down. So they're deactivating ortho-para directors. So that chart on the last one, I guess I'll put that up again. So electron donating groups So here are the three classes you have. Electron donating groups are ortho-pair directing and activating here, right? Electron donating, so methoxy, an N with a lone pair, an S with a lone pair, alkyl groups are going to be ortho-pair directing, activating groups. Electron withdrawing groups, carbonyls, any a carbon with a strong partial positive, or any atom that's got a full positive, it's going to be an electron withdrawing group, it's going to direct meta, and it's going to deactivate the ring. Chlorine, bromine, and iodine are going to be ortho-pair directing, but they're going to be deactivators.